Yeah, perfect. Yeah. Yeah. Yeah, it looks perfect. So it's a pleasure to welcome Professor Huang. And, many of, she's quite familiar to most of us here because, quite a few of our students, in fact, one student from Calcutta is going and joining with her. And if you look at her area, quantum metrology, quantum cryptography, quantum networks, they are all the kind of things what students all over India are interested. And, she has a very distinguished career. Before joining as a faculty, she was, she did her bachelor's in University of Sydney, basically product from Sydney, then went out University of Sheffield to UK, came back to Macquarie. Now she's a faculty, and she's associated with this Sydney, quantum initiative, and and presently in the physics and astronomy department of Macquarie University. And if you see her papers, extremely frontline works, and I'm actually very happy to see Professor Dowling's name because although he's no more, but we are all keen followers of his work. It's so nice to see that finally his name is also there in a collaboration of your work. So,
yeah, he was. So yeah, thank you for the introduction. So yeah, Professor Dowling was a dear mentor of ours, quite a few of us actually. So this is I guess my last piece of work with him was finally published after big fights with referees.
Yeah. Okay.
So yeah. So
you can talk it for 1 hour. Essentially, 50 plus 10, roughly 50 minutes or 55 minutes, and then some minutes per question and answer. So now you can start.
I don't think I'm going to take up the whole hour, but we'll see how it goes. I'm also happy to take questions in the middle if there are questions. Yes, so this piece of work goes under several names. They're all equivalent. So the more catchy title, which I'm using today, is Private Key Quantum Cryptography with Boson Sampling. We also call it Photonic data locking. And yeah, and I guess this paper was dedicated to John Dowling, who passed away 2 years ago in June. So here is a roadmap for where we're going. I will first introduce boson sampling, and then I will go into our security protocol. And then I'll tell you about quantum data locking, which is a uniquely quantum phenomenon that, that violates certain classical bounds. And then I will show you a sketch security proof. So what is boson sampling? And what is this connection with cryptography? So boson sampling is a non-universal model for quantum computing, and the task is this. So imagine we have a linear optical interferometer given by the unitary U. If we have m spatial modes and we have n input photons, the task is to send in these single photons into the interferometer, and the task is to sample the output. So we know that if we have n photon input Fock states, and the output photon distribution will be proportional to the permanent of the n by n submatrix of U. U as in the unitary. Now, if we have that the number of modes, m, is much larger than n, then Aronson and Arkhipov showed that this task is actually exponentially difficult to compute on a classical computer, what they call sharp p hard. And so this is why we think boson sampling is post-classical, and this is actually the first time that we have evidence, like concrete evidence, that a quantum computer may have an exponential speedup. So So to give some intuition as to why boson sampling is related to the matrix permanent, let's say we have a creation operator AI that is acted upon by some unitary, then it transforms the mode in this way. So for example, if we have two input photons at modes 1 and 2, the probability that they will get output at modes 2 and 3 is proportional to the probability that they both go straight through and the probability that they will cross over. And this term here is proportional to the permanent of that particular submatrix. And if you are not familiar with the idea of a permanent, it is simply the matrix determinant, except all the minuses are swapped to pluses. Okay. So since its conception, just about every large photonics group have tried to do a boson sampling experiment. So I believe to date, Jianwei Pan's group in China holds the record of using 20 photons in 60 modes where they sampled that Hilbert space of dimension 10 to the 14. Yeah, truly impressive work going on there. Okay, so what about cryptography and like what's the intuition there? Well, we know that at the output of a boson sampling device, the state has large photon number path entanglement. So the photon number is highly entangled with the path. We know that this is difficult to simulate classically if the number of photons is large enough. But what about by a quantum computer? Would it still work? So here we actually have the first information-theoretic proof that boson sampling is useful for cryptography. And by useful, we mean that we can either do efficient quantum key distribution, or we can encrypt a message that is longer than the key used to encrypt it. Okay, so, and later we actually move out of the boson sampling regime, that is a no collision regime. It just means that for doing boson sampling, we assume that the photon numbers are very dilute. If actually we're able to use make use of the Hilbert space a bit fuller, then we'll have a very efficient scaling of the Hilbert space. So we have something like a quantum enigma machine here. Yeah, and this term was coined by, I guess, Gu Haitao at this PRX paper. Yeah, so yep, so prior to us, there have been a couple of papers which have considered boson sampling inspired protocols for quantum metrology as well as quantum chemistry. But as far as I know, we are the first people to actually make use of the original boson sampling protocol. Cool. Okay, so I mentioned an enigma machine. So just a quick recap for those who are not familiar what it may be. So it is an encryption device that was extensively used by Nazi Germany during the Second World War. At the time, they were sending radio signals and they know that the Allies were intercepted. So any message would need to be protected or encrypted. So this, the design back then was essentially a substitution encryption where you're just swapping out letter of the alphabets. So here at the example, I say we swap out the A for the L and the B for the U and etc. etc. But what made it so difficult to crack for the technology at the time was that after each letter, the substitution rule would also change. Yeah, so at the time, this was difficult to crack, but obviously it was cracked at some stage. But in terms of, so if rather than classical messages, we have quantum states, then we also get the known cloning theorem on our side. So, so if you're trying to crack such a device, you can just do it by brute force, where you can turn it over and over again until you get the answer that you want, or an answer that makes sense, right? Whereas for quantum states, you get one measurement, and that's essentially where the security is coming from. Okay. So yes, oh wait, before I go on, so yeah, so how this works is that you have a copy of this device from the sender's perspective, and you have an identical copy of this device on the receiver's end. So you put in the plain text, and then ciphertext comes out, and then on the receiver end, you put in the ciphertext, and then plain text comes out because you know what the substitution was. So that's essentially how our protocol works, and we can now talk about it. This is our protocol. We have two communicating parties, Alice and Bob, who each hold their end of the interferometer. So to send a message, Alice uses the code words psi-x, and these are chosen from big M possible configurations. So big M is equal to M choose N, and this comes from the fact that we have N photons and M spatial modes. So each round there are log M choose N bits transmitted. Alice and Bob pre-share a K-bit secret key, so they are the only ones who know this secret key. In advance, but not necessarily secret, Alice and Bob agree upon a set of K random M by M unitary matrices, and we label these as UK. Alice encrypts the quantum state psi-x, so she prepares a state and inputs them here, and then she applies the unitary UK associated with the secret key, and she sends out the state. Bob, on the other hand, he applies U inverse and performs photon counting. So in this case, Alice applies UK, Bob applies UK dagger. So this interferometer turns into the identity, and Bob gets the message as Alice has transmitted. Okay, and I will show you the results first, and then I'll go into the security proof. Where'd it go? Yeah, so here we're defining a net secure communication rate as log M, which is the number of bits transmitted, subtract the log K, which is the number of secret bit used in the encryption. So log M is given by this solid blue curve over here, and log K is plotted at the bottom for different security parameters. And as you can see, so here we're using, we are in the boson sampling regime where the number of modes is equal to the number of photons cubed. And as we see, if as a function of n, there is an exponential gap between the number of messages transmitted and the number of secret bits consumed. So we've accomplished our task here. And now it remains to show how we actually got these numbers. And remember, this is only a single shot, right? So we have a single shot of photons going into the interferometer, and then a single shot of, and then Bob has applied the decryption, and then the message has been decrypted. I will talk about scaling up the protocol a bit later. So this is where I have to tell you about the framework under which our protocol was derived. We used technical results from the Arison and Arkham paper to calculate the key consumption, but the classical computational complexity of boson sampling itself is not required in the protocol. So this is actually a feature of our protocol because we just simply do not need to use many photons as boson sampling would require to see any quantum advantage. And yeah, so we go beyond the no collision regime, so the boson sampling regime. So later we will actually see that we can put in the number of modes comparable to, sorry, the number of photons comparable to the number of modes. And for this protocol, we actually using the accessible information as a security quantifier, and we are using the quantum data locking effect, that is. So the accessible information is a maximization over the mutual information. But so this has a drawback, which is that we have to impose the bounded quantum storage model. So here we're assuming that Eve have quantum memories, but they will collapse at a finite given time, but it is known. So it can be for as long as you like, but it has to be known and finite. Just so that we enforce that she has to make a measurement at some stage. Just a quick reminder on what the mutual information is for those of you who may not be familiar. So if you have a so if you have a random variable x, which has m outcomes, and each of these outcomes occurs with probability p of x, then the Shannon entropy of x is given by the summation over p of x times log of x. So now if you have two random variables, a and b, so here a may be, for example, Alice's source encoding, which are spitting out these code words, and b could be what Bob is measuring from the quantum state, or what Eve is measuring from the quantum state. We can define a mutual information I, A, and B, and this is equal to HA plus HB minus HA and B. And the accessible information between A and B is defined as the maximization over all possible measurements of the mutual information between A and B. So if B is held by Bob, the legitimate communicating party, you want I, A, and B to be large. But if B is, Eve, then you want I, A, B to be small. Okay. Are there any questions so far? Okay. So now I can tell you about the quantum data locking effect. So we know that this is the state that Alice is preparing. So it's a mixture of over the different code words. Average, yeah, so there were M code words, and Alice is sending randomly these messages. And because Bob has knowledge of the secret key, this is our notation. So we have the mutual information between Alice and Bob. So because Bob is holding Y, which is a measurement variable, and K, which is the security key, then that quantity is equal to log 2 of M. But since now Eve is missing log K bits of information, what is the mutual information between Alice and Eve? So what does Eve see? So Eve essentially sees Bob's state, except it's also now averaged over the different unitaries that are used for the encoding. So here we're averaging over K of them. So but what is this quantity? Classically, there is this theorem which states that if you're using K bits to do the encryption, then the mutual information difference between Alice and Bob and Alice and Eve is upper bounded by log 2K. So this is just another way of stating the one-time pad that if you're using K bits of secret key to encrypt a message that's longer, you will be able to encrypt at most K bits. On the other hand, there is a striking difference between the quantum and the classical, where this mutual information difference can be much, much larger than K. So this is known as the quantum data locking effect, and it is uniquely quantum, and there is no classical counterpart. Okay, so now we are able to go into the security proof, or a sketch of it. So the goal here, sorry, okay, so I'm seeing a question, why is there no not a factor of k in the denominator. Sorry, there should be a 1 over k here. Yes, that was my mistake. That's actually the first time it's been picked up. I've given quite a few of these talks. So yeah, good job in spotting it. Okay. Yeah, so the goal is to upper bound the mutual information, so the accessible information between Alice, who holds X, and Eve. And we want to bound this with high probability. So what we want to show is that X and E is smaller than 2 times epsilon times log of M. So remember, M is the message size. And so we're bounding this quantity here, which we have seen before. So it's maximized over all possible measurements that Eve can do. And so Bob sees this state, as we've seen before, and Eve sees this state. So yeah, so here's the factor k, as we've seen before. So I will just leave this state here. So the starting point is that all the different so what Eve can do is described by a set of POBM elements, which takes this form. So you have an element alpha y of phi, and then when you take a summation over y, this should add up to the identity. Sorry, there should be a subscript y here in this vector phi. Okay, so when you apply equation 11 to equation 10, you end up with a term that looks like this. So we have this top term and this bottom term, and we're going to bound these 2 terms separately. Okay, so to bound the top term, so remember this is a matrix here, we are going to use the matrix Chernoff bound. So for the matrix Chernoff bound, what it states is that, so given that you have Hermitian matrices, so XT are Hermitian matrices and their IID, and expectation values, if we average over them, is mu. And so for us here, mu would correspond to the maximally mixed state. And then so the theorem states that if you add up or if you average over T of these matrices, then the probability that the end state deviates from the expectation value by delta, which is a small number, is exponentially suppressed in terms of the number of terms you add, and it scales as the deviation squared. So after some algebra, we end up showing that the first term there is with high probability not deviated that much from the maximum mixed state. So this is 1 plus epsilon. Epsilon is a small number, and rho E bar is our maximum mixed state. And then to bound the second term, we're going to use a tail bound from Maurer. So this is a very similar statement to the matrix Chernoff bound, except it applies to scalar variables as opposed to matrices. So once again, if you have xk equal to some IID non-negative real variable, then if you add up k of these, the probability that it is the probability that the sum is smaller than 1 minus, say, tau, is once again exponentially suppressed in terms of the number, the deviation, and there's this value here, which is the second expectation value of the second moment divided by the first moment squared. Now, this term we call gamma, which is actually a very important factor because it corresponds to the asymptotic key rate that is needed for the encryption. And so if we are in the Boson sampling regime, this comes out analytically. If we're not in the Boson sampling regime, then potential photon bunching effect would modify this number. So this is also where our protocol ties into the boson sampling protocol. So in order to calculate the key consumption rate gamma, we need to calculate the overlap of a generic vector phi with the unitary applied to the code words. And this is proportional to the permanent squared. And we can calculate this number analytically quite easily. And then we also need this quantity squared, or the fourth moment of the permanent, which we've extracted from the original Aronson-Ackoff paper. And gamma is shown to be less than 2 times n plus 1. And so, yeah, so this is why like the boson sampling protocol is so efficient in the encryption. So because we have a Hilbert space that is scaling exponentially in m and n, but the secret consumption rate is only dependent, it's linearly dependent on n. So the key rate is equal to log of that. Okay, so if we have photon bunching, then we have to calculate this quantity numerically, which we can do for small numbers. But we actually have a conjecture that can deal with large numbers as well. Okay, yeah, so, and then to complete a security proof, we account for photon bunching. We need to extend the protocol to all the different possible code words. And then we need to use something called an epsilon net to extend it to all of the vectors that Eve can use. And after about 10 pages of maths, we end up showing that the mutual information between Alice and Eve is indeed upper bounded by 2 times epsilon times log m, provided the secret keys log k is larger than log of gamma plus log d over m. So d is the entire Hilbert space of the m modes and n photons. This is slightly larger, well, okay, slightly or much larger than m, depending on what you use, plus some term which is of order log 1 over epsilon. And the probability of failure of the protocol is given by this complicated expression over here. But the only thing that I want to draw your attention to is that this entire expression sits inside an exponential. So provided k is larger than this expression over here, then the probability of failure goes to 0 very, very quickly. And it turns out that if you have k equal to this term, which we derived in the paper, see the paper for detail if you are interested, then log of k is equal to this expression here, which we've seen before, and that's how we got it from. So provided log k is larger than this number by a small amount, the protocol would fail with very, very small probability. Okay, so obviously everything I've described so far is a one-shot protocol. And for a quantum communication protocol, obviously you don't want something that's one-shot. Here you want to transmit many, many signals and decode them many times. And so Alice's signal will look something like this. So you have a signal train. It turns out that the maths works out very nicely. So there's nothing else complicated. So the encryption that you need just adds up per transmission that you need. Okay, but does the protocol still work in the presence of losses? Because so with linear optics, it's obviously not very useful if the protocol breaks as soon as there is a tiny bit of loss. Turns out that yes, it still works. So for this particular configuration of 20 modes and 4 photons, so these are now very modest numbers now. We have plotted the net communication rate as a function of loss. So for these purple circles, we have perfect transmission. for transmission parameter equals to 0.7, we have, we have this. So for eta equals to 90%, we have this green. And for this red, we are at transmission parameter 70%, and we are just above 0 if we have transmission parameter equals to 0.5. Now, so the referee at this point asked, what about how does it compare to BB84? Okay, so I think before I show you that graph, I'll tell you how we got how we dealt with losses. So yeah, so for a lossy channel with transmissivity eta, we can calculate the mutual information between Alice and Bob. It essentially starts from why don't I use the whole level information to bound the accessible information linked to Eve? So so I think, yeah, so we're yet to do that. So the lazy answer is because we know that the accessible information works, or we anticipated it works, therefore we did it. I mean, please feel free to investigate the whole level information if you like. Yeah, so if Alice sends n photons, then Bob will receive k of them with probability given by this binomial distribution, and we can calculate the mutual information between Alice and Bob analytically. So we have these very nice expressions for what happens with losses. So all loss does is to reduce the communication rate, but it doesn't leak anything in particular to Eve, because our protocol is a direct reconciliation protocol where all the information is encrypted at the point of transmission. Yeah, so one of the referee asked, how does it compare to BB84? So I'm actually really glad that they asked, because that gave us our money shot over here. So let's talk about BB84 first. So we're talking about discrete variable BB84 using 2 modes in the most optimal sense. So we're using, let's say so this is when the protocol is already using the bias spaces almost all the time. So BB84 can transmit at most 0.5 bits per mode. So you have 2 modes and you're transmitting at most 1 bit of information. If you're using the symmetric case, then BB84 actually transmits a quarter of a bit per mode. So because our protocol is a direct reconciliation protocol, therefore it makes more sense to compare it to direct reconciliation BB84. And the direct BB84 and direct is plotted in this red solid curve over here. But for reference, I will leave the BB84 in reverse reconciliation in orange. So here we're using, so the green curve is for 20 modes optimized over the number of input photons as a function of loss. So there's a trade-off here. So the trade-off is between the number of secret key needed for the encryption, the number of bits that gets transmitted, and it's balanced by losses. And if you use 40 modes, then our curve plotted in blue here actually sits above BB84 for all values of the transmission parameter. And we expect that if we were to do our protocol in reverse reconciliation, we can actually beat BB84 in terms of the information density for all parameters of eta, but we haven't done that yet. So yeah, so the reason why we can potentially beat BB84 is because, so for BB84, for each time you do a transmission, your photon is restricted to in between these 2 lanes, right? Whereas for our protocol, we are allowing our photons to use all the different spatial modes. And to be more quantitative, we have that log m choose m divided by m bit could be larger than 2. Sorry, could be larger than 0.5. So that's why our protocol could potentially be larger than BB84. Yeah, so in summary, we have a quantum private key encryption protocol, which is the first actual application of boson sampling. We have an information-theoretic a security proof that holds for any number of modes m and any number of photons n. Yeah, so in the future, some interesting things that could be considered would be to try and remove the need for the bounded storage model. We might want to look at scattershot quantum data locking and use weak coherent states just because they're much easier to make in the lab. We might want to look at error correcting codes and privacy amplification and so time-binding encoding for long distance communication. Okay, so I put that on there because so we think about boson sampling by using spatial modes, which is very intuitive, but actually we don't really need spatial modes. We can do it in orbital angular momentum or time-binding encoding or any other encoding that you like, provided you can manipulate the unitaries. So, and yeah, time-binding encoding might actually give you slightly more phase stability. So giving credit where it is due, I guess the protocol, so I wasn't there when the protocol was first conceived, or the idea was first conceived. So it was conceived by our late mentor, John Dowling and Peter Rody and Dominic Berry a couple of years back in Sydney somewhere. But we have no idea how to do the security proof until Cosmo Lupo came along. And I would like to end the talk by this small story over here. So as John would tell it, so he was telling us about the story of how when Yang and Lee, you know, who obviously got the Nobel Prize, when they were doing their papers together, they would alternate between who's the first author. But when they completed the work on symmetry breaking and they knew that it would lead to a Nobel Prize, one went to the other and said, I know it is your turn this time to be the first author, but actually I would like it to be me. And turned out that they never spoke to one another again, apart from at Nobel Prize ceremony where they shook hands. So, you know, John told it as a very sad story, and that quote followed. And yeah, so I would like to thank him for his encouragement and enthusiastic support over the years. Oh, and yes, I would like to do some shameless advertisement. We are also organizing a conference in the memory of John that is happening in real person in Sydney early January next year. The registration will be free, and this will be in person. Okay. Okay, so I see another, and then at this point, I'll be happy to take your questions. And I see another question. Does this protocol have the 3 dB loss limit similar to direct reconciliation CVQKT? Oh, I am actually not an expert on CVQKT, but I guess not. If you look at this graph, then we are able to transmit some information past the 0.5, as in the 3 dB mark. So I am not entirely sure, but we can have a look at it. What is the complexity of decoding? Oh, so there is no complexity in the decoding, apart from when you're trying to use codes. So the encoding is a linear optical unitary, and the decoding is another linear optical unitary. So I think the part that is slightly more complicated would be when we start having losses and need to use codes for the code words, but that should all be in classical coding theory. Yeah, so yeah, so the paper is on the I guess on open access, published in Quantum. So if you're interested, or if you want to, please send me an email.
Okay, so thank you, Professor Huang.
Thank you.
If we have more questions, we will write to you also, because your works are quite exciting.
Thank you.
Okay, there's a question from you, Mr. Kundu. Is it necessary that the unitaries UK are, you can open yourself and ask.
Oh, right. No, the unitaries UK, so the actual set of unitaries do not need to be unknown. So it's like basic. It's like, think about BE84, right? So you have the Z basis or the X basis. Those two are both known to Eve. Eve just doesn't know which base is used. So the unitaries can be open, but they just need to not know which one was chosen at the time.
Any more questions?
Awesome. Yeah. Thank you very much for the invitation and for your attention.
Sure. Thank you so much.